Here is the opening section of the YouTube video script. Intro music plays and the host appears on screen with a friendly smile. Host. Have you ever wondered how self-driving cars detect objects in real time? Let's dive into the world of computer vision and explore how OpenCV can be used to build a real-time object detection system. Visuals of self-driving cars and computer vision applications appear on screen. Host. Computer vision is a rapidly growing field that enables computers to interpret and understand visual data from images and videos. It has numerous applications, from surveillance and security to healthcare and robotics. One of the most exciting applications of computer vision is real-time object detection, which enables systems to detect and track objects in real time, making it a crucial component of autonomous vehicles, drones, and smart cities. Visuals of OpenCV logo and its applications appear on screen. Host. In this series, we'll explore how to build a real-time object detection system using OpenCV, a widely used computer vision library. We'll delve into the fundamentals of object detection, explore popular algorithms like YOLO and SSD, and learn how to integrate them with OpenCV. By the end of this series, you'll have a solid understanding of how to build your own real-time object detection system using OpenCV. Here is section 2 of the script. Now that we've got a sense of what we're trying to achieve, let's take a step back and explore the basics of computer vision. Computer vision is a field of study that enables computers to interpret and understand visual data from images and videos. At its core, computer vision involves three key steps: image processing, feature extraction, and object recognition. Image processing refers to the techniques used to enhance and transform images, such as resizing, thresholding, and filtering. This step is crucial in preparing the image for further analysis. Feature extraction involves identifying and extracting relevant features from the image, such as edges, shapes, and textures. These features are then used to train machine learning models to recognize objects. Object recognition is the final step, where the system uses the extracted features to identify and classify objects within the image. This is where object detection comes in, the ability to locate and classify objects in real time. Computer vision has numerous applications in real-world scenarios, such as self-driving cars, surveillance systems, and medical imaging. In the context of object detection, computer vision enables us to detect and track objects, such as pedestrians, cars, and road signs. By leveraging computer vision techniques, we can build robust and accurate object detection systems. In the next section, we'll dive deeper into OpenCV, a powerful computer vision library that will be our primary tool for building our real-time object detection system. Here's section 3 of the script. Welcome back. Now that we've explored the basics of computer vision and object detection, let's dive into the powerful tool that will help us bring our real-time object detection system to life: OpenCV. OpenCV, or Open Source Computer Vision Library, is a widely used, open-source library that provides a comprehensive set of computer vision and machine learning algorithms. With support for multiple programming languages, including C++, Java, and Python, OpenCV is the perfect choice for building cross-platform applications. What makes OpenCV so powerful? For one, it has an extensive range of features, including image processing, feature detection, and object recognition. It also has a vast array of pre-trained models and algorithms, such as HAR cascades and deep learning-based methods, that can be used for object detection. Plus, OpenCV is highly optimized for performance, making it perfect for real-time applications. Real-world examples of OpenCV in action include self-driving cars, facial recognition systems, and even medical imaging analysis. And the best part, OpenCV is completely free and open source, making it accessible to developers of all levels. In the next section, we'll show you how to set up your development environment and start using OpenCV to build your real-time object detection system. Here is section 4 of the YouTube video script. Welcome back. Now that we've introduced OpenCV, it's time to set up our development environment. To build a real-time object detection system, we'll need a few tools and libraries. First, we'll need Python 3.6 or higher, which is the recommended version for OpenCV. Next, we'll install OpenCV using pip, the Python package manager. Simply open your terminal and type pip install OpenCV Python. We'll also need a code editor or IDE, such as Visual Studio Code or PyCharm, to write and debug our code. Once you've installed OpenCV in your IDE, let's configure the IDE to work with OpenCV. In Visual Studio Code, for example, we'll need to install the Python extension and configure it to use the Python interpreter that we installed OpenCV with. This will allow us to write and run our OpenCV code directly from the IDE. Finally, let's create a new project folder and add a Python file, such as object_detection. py, where we'll write our object detection code. We'll also need some sample images or videos to test our object detection system, which we can download from datasets like ImageNet or Coco. With our environment set up, we're ready to start building our real-time object detection system with OpenCV. In the next section, we'll show you how to load and pre-process images using OpenCV. Welcome back. Now that we have our environment set up, let's dive into the exciting part, loading and pre-processing images using OpenCV. This step is crucial in preparing our images for object detection. First, we need to load our images. We can use OpenCV's imread function to read images from various formats, such as JPEG, PNG, or even videos. For example, we can load an image of a car using img=cv2. Imread, car, JPG. Next, we need to pre-process our images to enhance their quality and prepare them for object detection. One common technique is resizing. We can use OpenCV's resize function to resize our image to a specific width and height. For instance, img=cv2. Resize, img, 800, 600. Another important step is thresholding. We can use OpenCV's threshold function to convert our image into a binary image, where pixels are either 0 or 255. This helps to separate the object from the background. We can also apply filtering techniques, such as Gaussian blur or median blur, to reduce noise and improve image quality. By applying these pre-processing techniques, we can significantly improve the accuracy of our object detection system. In the next section, we'll explore popular object detection algorithms and their trade-offs. Here's section 6 of the YouTube video script. Object detection algorithms. Now that we have our images pre-processed, let's dive into the world of object detection algorithms. These algorithms are the brain behind our object detection system, responsible for identifying and locating objects within an image. There are several object detection algorithms to choose from, each with its strengths and weaknesses. Haar cascades, for instance, are a popular choice for detecting faces and other simple objects. They work by applying a series of filters to an image, detecting edges and features that are indicative of an object's presence. HOG+SVM, on the other hand, is a more complex algorithm that uses histograms of oriented gradients to detect objects. This algorithm is particularly useful for detecting objects with complex shapes, such as pedestrians or cars. Deep learning-based methods like YOLO and SSD are another popular choice for object detection. These algorithms use neural networks to detect objects, and are often more accurate than traditional computer vision techniques. When choosing an object detection algorithm, it's essential to consider the trade-offs between accuracy, speed, and computational resources. For example, Haar cascades are relatively fast and efficient, but may not be as accurate as deep learning-based methods. In the next section, we'll implement a simple object detection system using Haar cascades, and explore how to train and test the classifier. Welcome back to our tutorial on building a real-time object detection system with OpenCV. In the previous section, we discussed popular object detection algorithms, including Haar cascades, HOG+SVM, and deep learning-based methods. Now, let's dive deeper into Haar cascades and implement a simple object detection system using this algorithm. Haar cascades are a type of classifier that use a cascade of weak classifiers to detect objects in images. They are fast and efficient, making them suitable for real-time object detection. To implement Haar cascades, we'll use OpenCV's built-in functions, such as CV2. Cascade classifier. First, we need to load the pre-trained Haar cascade classifier for face detection. We'll use the Haar cascade _frontal face _default XML file that comes with OpenCV. Next, we'll load an image and convert it to grayscale, as Haar cascades work with grayscale images. Now, let's use the CV2. Detect multi-scale, function to detect faces in the image. This function takes the grayscale image, the classifier, and a few other parameters as input and returns a list of rectangles that represent the detected faces. We can then draw these rectangles on the original image using OpenCV's CV2 rectangle function. Finally, we can display the output image using OpenCV's CV2 IMShow function. By implementing HAR cascades, we've built a simple object detection system that can detect faces in images. In the next section, we'll explore how to use pre-trained models, such as YOLO and SSD, for real-time object detection. Now that we've built a simple object detection system, let's take it to the next level by leveraging pre-trained models. In this section, we'll explore how to use popular pre-trained models like YOLO, or You Only Look Once, and SSD, or Single Shot Detector, for real-time object detection. YOLO and SSD are two of the most widely used pre-trained models for object detection. They're incredibly powerful and can detect a wide range of objects, from pedestrians and cars to animals and products. The best part is that they're already trained on massive datasets, so we don't need to collect and label our own data. To get started, we'll need to download the pre-trained YOLO or SSD model and integrate it into our system. This can be done using OpenCV's DNN module, which provides a simple way to work with pre-trained models. We can then use OpenCV's video capture and processing capabilities to feed video frames into the model and get real-time object detection results. Using pre-trained models like YOLO and SSD can significantly improve the accuracy and speed of our object detection system. They're also highly optimized for performance, making them perfect for real-time applications. In the next section, we'll explore how to achieve real-time object detection using OpenCV's video capture and processing capabilities, and optimize our system for performance. Now that we've explored pre-trained models for real-time object detection, let's dive into the nitty-gritty of achieving real-time performance using OpenCV. To capture and process video in real time, we'll utilize OpenCV's video capture class, which allows us to read frames from a variety of sources, including cameras, files, and even IP cameras. We'll also use OpenCV's IMShow function to display the output in real time. To optimize our system for performance, we'll employ techniques such as downsampling, which reduces the resolution of the input video, and frame skipping, which skips processing every nth frame. For example, if we're using a high-resolution camera, we can downsample the video to reduce the computational load. We can also use OpenCV's set function to adjust the camera's exposure and gain settings, which can improve the quality of the input video. To demonstrate real-time object detection, let's use a sample video of a busy street scene. We'll use the YOLOv3 model, which is pre-trained on the COCO dataset, to detect objects such as cars, pedestrians, and bicycles. As we process each frame, we'll draw bounding boxes around the detected objects and display the output in real time. With OpenCV's video processing capabilities, we can achieve smooth and efficient real-time object detection, making it perfect for applications such as surveillance and robotics. Now that we have a solid foundation for real-time object detection, let's take it to the next level by exploring some advanced techniques to improve the accuracy and efficiency of our system. One technique is non-maximum suppression, which helps eliminate duplicate detections and reduce false positives. We can use OpenCV's built-in CV2 DNN NMS boxes function to implement this. Another technique is tracking, which allows us to follow the movement of detected objects across frames. We can use the Kalman filter, a mathematical algorithm that estimates the state of a system from noisy data, to predict the position of objects in the next frame. OpenCV provides an implementation of the Kalman filter in the CV2 Kalman filter class. We can also optimize our system by using techniques such as multithreading, which allows us to process multiple frames simultaneously, and GPU acceleration, which leverages the power of graphics processing units to speed up computations. For example, we can use OpenCV's CV2 UMOT class to take advantage of GPU acceleration. By incorporating these advanced techniques, we can significantly improve the performance and accuracy of our real-time object detection system, making it suitable for demanding applications such as autonomous vehicles and smart surveillance systems. Here is the closing section of the YouTube video script. That's it for today's tutorial on building a real-time object detection system with OpenCV. As we've seen, by leveraging the power of computer vision and machine learning, we can create a robust and efficient system that can detect objects in real time, even in complex environments. The key takeaway from this tutorial is that by fine-tuning our model and optimizing our system's performance, we can significantly improve the accuracy and efficiency of our real-time object detection system, making it suitable for demanding applications such as autonomous vehicles and smart surveillance systems. As we conclude this tutorial, we hope you now have a solid foundation in building real-time object detection systems with OpenCV. If you've enjoyed this video, please give it a thumbs up and share it with your friends who are interested in AI and computer vision. We'd love to hear your thoughts and feedback on this tutorial, so please drop a comment below and subscribe to our channel for more AI insights. What do you think? Drop a comment below and subscribe for more AI insights. Quote.